Take a moment to look at the device you're using right now. Whether it is a smartphone, a tablet, a powerful desktop computer, it represents the pinnacle of decades of technological evolution. Inside its sleek casing, billions of microscopic switches called transistors are flipping on and off, processing information at unimaginable speeds. These tiny components are the heart of our digital world, the engines that power everything from streaming videos to complex scientific simulations. They operate on a simple yet profound principle: controlling the flow of electrons. It's a symphony of electrical charge, a dance of negative particles orchestrated with breathtaking precision to create the reality of our connected age. For over 70 years, this has been the undisputed foundation of computing. We have mastered the art of herding electrons, using their electrical charge to represent the ones and zeros of binary code. We push them through silicon pathways, trap them in memory cells, and read their presence or absence to retrieve our data. This relentless pursuit of smaller, faster, and more efficient electronics has given us the modern world. It is a story of incredible human ingenuity, a testament to our ability to harness the fundamental forces of nature. But what if this entire digital civilization, this vast and complex technological ecosystem, has been built upon only half of what the electron has to offer? This isn't a riddle or a philosophical question. It is a very real and fascinating puzzle at the forefront of modern physics and engineering. The electron, the tiny particle that serves as the workhorse of all our electronics, possesses more than just its familiar negative charge. It carries another property, an intrinsic quantum characteristic that is just as fundamental, but has been largely ignored by the computers we use every day. Imagine building a global transportation network using only roads, completely unaware that every vehicle also has the built-in capacity to fly. For decades, our computers have been grounded in the same way, using only one aspect of the electron's nature. The implications of this oversight are staggering. As we push the limits of traditional electronics, we are running into fundamental barriers of physics. Our devices get hotter, they consume more power, and shrinking them further becomes exponentially more difficult. The very foundation of Moore's law, the idea that computing power doubles every 2 years, is beginning to crumble. This is where our story truly begins. We are on the cusp of a potential revolution, one that doesn't just seek to improve our current technology, but to fundamentally change its operating principles by unlocking the other half of the electron, a hidden quantum secret known as spin. So, what is this mysterious other half? It's a quantum property called spin. The name can be a little misleading. When physicists first discovered it, they imagined the electron as a tiny spinning ball, like a miniature planet rotating on its axis. This simple picture helped explain some of its behavior, but we now know it's not physically spinning at all. Spin is something deeper, more fundamental, and far more bizarre. It is an intrinsic built-in property, like the electron's mass or charge. You cannot stop it or change its amount. You can only observe its orientation, which comes in two distinct flavors: spin up, spin down. This is the quantum twist that changes everything. While conventional electronics only care about whether an electron is present or absent, a new field called Spintronics cares about both its presence and the direction of its spin. This simple addition of a second property opens up a vast new landscape of possibilities for processing and storing information. Instead of just using the electron's charge to represent a 1 or a 0, we can now use its spin as well. This dual-channel approach offers a fundamentally new way to design electronic devices, one that is not just an incremental improvement, but a complete paradigm shift in how we think about computing. This journey will take us from the familiar world of electrical currents and silicon chips into the strange and beautiful domain of quantum mechanics. We will explore how a technology born from this idea is already inside the hard drive of your computer, allowing it to store terabytes of data in a space smaller than your hand. This discovery, known as giant magnetoresistance, was so transformative that it earned its creators the Nobel Prize in Physics in 2007. It was the first major success story of spintronics, proving that controlling electron spin was not just a theoretical curiosity, but a powerful tool for real-world engineering. Our exploration will be a visual one, moving from the concepts you already know to the new ideas that could shape our future. We will decode the language of spintronics, not with dense equations or textbook lectures, but through clear storytelling and cinematic visuals that bring these invisible quantum phenomena to life. We will build our understanding from the ground up, step by step, to reveal how manipulating this tiny quantum property could lead to computers that are not only faster, but also drastically more energy efficient. This is the story of spintronics, the tiny quantum revolution that could change computing forever. To understand how our digital world works, we must first look at the materials it is built from. Everything around us, the air we breathe, the chair you are sitting on, is made of atoms. These are the fundamental building blocks of matter, tiny structures composed of even smaller particles. At the center of every atom is a dense nucleus, containing positively charged protons and neutral neutrons. Swirling around this nucleus in a cloud of probability are negatively charged electrons. In most materials, these electrons are tightly bound to their individual atoms, like planets orbiting a star. But in some materials, particularly metals like copper, the outermost electrons are not so loyal. These electrons are free to roam, detached from any single atom. They form what can best be described as a vast sea of charge, flowing freely throughout the material. This collective of wandering electrons is what makes metals such excellent conductors of electricity. Now, imagine this sea of electrons is like a perfectly still river. The potential for a powerful current is there, but nothing is moving yet. To get the water flowing, you need to create a difference in height, a slope for the river to follow. In electronics, we create a similar slope using a voltage source, like a battery. A battery has two terminals, a positive one and a negative one, creating an electrical pressure. When we connect a wire to this battery, the negative terminal, rich with excess electrons, pushes them into the wire. At the same time, the positive terminal, with a deficit of electrons, attracts them. This push and pull creates an electric field that urges the entire river of electrons to begin flowing in a single, coordinated direction. This directed flow of electrons, this river of charge, is what we call an electric current. It is the lifeblood of electronics, powering everything from a simple light bulb to the most complex supercomputer. The movement itself is surprisingly slow, but the signal travels at nearly the speed of light. This simple act of controlling the flow of charge is the first and most crucial principle of electronics. By creating pathways for this current to travel, we can move energy and information from one place to another. We build intricate circuits, like tiny road networks, to guide the electrons exactly where we want them to go. But simply having a current flow is not enough to build a computer. To perform calculations and store data, we need more than just an on state. We need a way to control the flow, to stop and start it with incredible speed and precision. We need a gatekeeper for our river of charge. The key to digital computing is switching current on and off. The revolution arrived with the transistor. The transistor is arguably the most important invention of the 20th century. It is a microscopic switch with no moving parts, crafted from a special material called a semiconductor, most commonly silicon. Silicon is the magic ingredient because it is not quite a conductor, like copper, and not quite an insulator, like glass. Its ability to conduct electricity can be precisely controlled, which makes it the perfect material for a gatekeeper. Imagine our river of charge, the flow of electrons, needs to cross a channel. A transistor acts like a gate across this channel. The transistor itself has three main parts: source, drain, and gate. In its natural state, the silicon channel between the source and drain acts as an insulator, preventing the current from flowing. The gate is closed and the river is blocked. To open the gate, we do not use a mechanical lever. Instead, we apply a small electrical charge to the gate terminal itself. This tiny charge on the gate creates an electric field that dramatically changes the properties of the silicon channel below it. It's like waving a magic wand that transforms the insulating silicon into a conductor. Suddenly, the blockage disappears, and the river of electrons can flow freely from the source to the drain. The switch is now on. When we remove the small charge from the gate, the electric field vanishes, the silicon channel returns to its insulating state, and the flow of current stops. The switch is off. This is the beautiful simplicity of the transistor. A tiny electrical signal controls a much larger electrical current. This process can happen billions of times every second. Think about that. Billions of microscopic gates open and close in concert. The processor in your device packs billions of these silent switches working together. This massive army of switches, each capable of being either on or off, forms the physical basis for all digital logic and memory. It is how our computers think, remember, and communicate with the world. A world of ones and zeros. This simple concept of a switch being either on or off is the foundation of the binary language that all computers speak. When a transistor is on and current is flowing, we can represent that state with the number 1. When it is off and no current is flowing, we represent that with the number 0. These two digits, 1 and 0, are the letters of the digital alphabet. Every piece of information in your computer, from the text of an email to the colors of a photograph, from the sound of music to the instructions of a software program, is ultimately encoded as a vast sequence of these ones and zeros, or bits. By arranging transistors in specific configurations called logic gates, we can make them perform simple mathematical operations. For example, we can build a circuit that will only produce a 1 at its output if both of its inputs are also 1. This is called an AND gate. We can build another circuit that produces a 1 if either of its inputs is a 1. This is an OR gate. From these simple building blocks, engineers can construct progressively more complex circuits capable of performing any calculation imaginable. Your computer's central processing unit, or CPU, is essentially a staggering collection of billions of transistors wired into an intricate web of these logic gates. Memory works on a similar principle. In the most common type of computer memory, called DRAM, each bit of information is stored by trapping a small packet of electrons in a tiny bucket called a capacitor, which is paired with a single transistor. If the capacitor is charged with electrons, it represents a 1. If it is empty, it represents a 0. The transistor acts as the gatekeeper, controlling access to the capacitor, allowing the system to either read its state or change it. This allows your computer to hold the data it is actively working on, like the operating system and the applications you are running. The problem with this type of memory is that the tiny capacitors are leaky. The charge that represents a 1 gradually trickles away in milliseconds. To prevent the data from being lost, the computer must constantly read every bit and then rewrite it, a process called refreshing. This is why it is called dynamic RAM. It requires constant power and attention to maintain its state. If you turn off the power, all the capacitors discharge completely and all the information vanishes instantly. This is known as volatile memory, a fundamental limitation we have lived with for decades. The inevitable heat. This entire system, this intricate dance of charging and discharging, of switching currents on and off billions of times a second, has a fundamental and unavoidable side effect: heat. Every time a current flows through a material, even a good conductor, the moving electrons inevitably collide with the atoms of the material. Think of our river of charge again. Even in a clear channel, the water molecules still bump into each other and the riverbed, creating friction. In electronics, these countless microscopic collisions convert some of the electron's electrical energy into thermal energy, which we perceive as heat. Each transistor switch consumes a tiny pulse of energy. Multiply those pulses by billions of transistors switching billions per second, and the energy quickly becomes waste heat. This is why powerful computers need elaborate cooling systems, from the small fan in your laptop to the complex liquid cooling pipes in a high-performance gaming PC or the massive air conditioning units in a data center. For decades, the answer to building more powerful computers was simply to make the transistors smaller and pack more of them onto a single chip. Smaller transistors are more efficient. They can switch faster and use less power per switch. However, as we cram more and more of them into the same tiny area, the overall heat density, the amount of heat generated in a given space, skyrockets. We are now reaching a point where we simply cannot remove the heat fast enough. This heat wall is one of the greatest barriers to future progress in conventional electronics. We are pushing the boundaries of what is possible with charge-based electronics. The power consumption of our global digital infrastructure is immense and growing. The heat generated limits the performance of our devices, and the volatile nature of our primary memory systems means they constantly leak power just to hold on to information. We have built a digital world on the magnificent but limited principle of controlling the electron's charge. To move forward, to build the next generation of computing, we may need to look beyond the flow of the current and ask what else the electron can do for us. The quantum compass. We have seen how our entire digital world is built upon controlling the flow of electron charge. It's a powerful idea that has taken us incredibly far. But the electron has another secret, a property conventional electronics ignores. This property is called spin. To understand it, we leave classical physics and step into quantum mechanics. Particles like electrons don't behave like tiny billiard balls. They follow a completely different set of rules. Spin is the most famous and important of those rules. Imagine a tiny, perfect compass needle. It always points north. Electrons have an intrinsic magnetic moment, like a built-in compass with north and south. That magnetism comes from spin. Spin gives rise to that magnetic moment. Every electron carries its own microscopic compass needle. This can't be turned on or off. It's fundamental to the electron, just like its negative charge and its mass. It's a permanent feature. Now quantum weirdness begins. You might expect the compass to point any direction, north, south, east, west, or anything in between. But it can't. In a magnetic field, the electron's internal compass must choose. It can only point in one of two directions relative to the field, aligned with the field, spin up, or opposite the field, spin down. No in-between options. This binary, two-state nature is a revelation. Traditional electronics builds 1 and 0 by stopping or starting current with transistors. The electron already has a natural binary. Spin up and spin down can encode information without moving charge, a natural binary at the single electron level, a new alphabet waiting to be read. It is crucial to be very clear about one thing. Despite its name, an electron is not literally spinning. The name spin is a historical accident, a relic from the early days of quantum theory. Early physicists tried to make sense using familiar classical ideas. They observed the electron behaved as if it had angular momentum, a property a spinning object has, like a planet, like a frisbee. The name stuck, but the analogy is deeply misleading. A classical spinning ball could spin faster or slower, but an electron spin has a fixed, unchangeable magnitude. Spin is intrinsic, like charge, a defining property of an electron. In the same way, you can't ask why an electron has spin. It's a fundamental quantum number. This has real physical consequences. Because it's not a physical rotation, spin doesn't have to obey all the same rules as a spinning top. This intrinsic nature makes it robust. Unlike the charge in a leaky capacitor that must be refreshed, an electron's spin state, up or down, is a permanent quantum property. It does not just fade away. Once set, it tends to stay unless flipped by a magnetic field or another particle. This stability is incredibly appealing for building memory. It opens the door to non-volatile memory systems that keep information with the power off, dramatically reducing energy waste. So we must abandon the image of a tiny spinning ball. Instead, we should embrace the abstract but more accurate picture. Spin is a fundamental, two-level quantum system that gives the electron a magnetic personality. Spin is a natural binary. The challenge is controlling and reliably reading that state, the electron's native language of spin. In conventional electronics, we are obsessed with the flow of charge, which we call an electric current. Spintronics adds a new idea, a spin current, the flow of spin. It is a fundamentally different kind of current, one that does not necessarily involve the net movement of any electrical charge. Picture people with spinning tops. One flip triggers the next. A wave of flips moves along. People stay put. Information, the flip, has moved from one end to the other, but none of the people have actually swapped places. A pure spin current can work in a similar way. It can be a flow of spin information without a corresponding flow of electrons. It's the transfer of angular momentum through a material, a cascade of spin flips propagating like a wave. Of course, in many spintronic devices, we do move the electrons themselves. But here, we create what is called a spin-polarized current. Instead of a random mix of spin-up and spin-down electrons flowing together, a spin-polarized current is one where there is a majority of one type of spin. A current can be mostly spin-up. That imbalance itself carries information. Engineers create and control spin currents with clever methods, most simply passing current through a permanent magnet acting as a spin filter. It preferentially allows electrons with one spin orientation to pass through while scattering or blocking electrons with the opposite spin. What emerges on the other side is a current with a net spin polarization, ready to be used in a spintronic device. This ability to generate spin-polarized currents is the first essential step in building a spintronic circuit. So we can create a current with a majority of spin-up or spin-down electrons. That's a great first step, but it's useless unless we can detect that polarization. We need a spin detector, a way to read the information encoded in spin. We read spin via magnetism. Spin gives a magnetic moment, tightly linking electrons to magnetic materials. This connection is the key to reading and to writing spin information. Spin up aligns with the field. Spin down opposes it. That distinction shapes transport through magnetic layers. That alignment, or not, dramatically affects how easily the electron travels through a magnetic material. Aligned spins pass through with very little resistance. It's like a friendly handshake, agreement, clear path. Anti-aligned spins suffer much more scattering. The magnetic moment clashes with the material's structure. It's like trying to swim against a strong current. The electron gets knocked off course and struggles to contribute to current flow. This is spin-dependent scattering. It means the electrical resistance depends critically on electron spin. This is the breakthrough. We can translate spin into a classical, measurable signal, electrical resistance. Measure a magnetic layer's resistance with a spin-polarized current, low when aligned, high when anti-aligned. We have built a spin detector. We can read the up or down message carried by electrons, bridging quantum spin and classical meters and circuits. The Spintronic toolkit, writing with spin. We can now generate a spin-polarized current, write, and detect its orientation, read. With these tools, we have the basic building blocks for a complete spintronic system. The ability to write information using spin opens up several exciting possibilities. The most direct method involves using a magnetic field. Just as a large magnet can influence a compass needle, a localized magnetic field can be used to flip the magnetic orientation of a tiny region of a material, effectively writing a bit of data. A more advanced and efficient technique for manipulating spin is called spin transfer torque. This is a remarkable effect where a spin-polarized current can itself alter the magnetic state of a material without needing any external magnetic field. Imagine firing a stream of spin-up electrons into a small magnetic layer. If this layer is currently oriented down, the electrons that pass through it transfer some of their angular momentum to the layer. If the current is strong enough, this continuous transfer of momentum can exert a powerful torque that physically flips the magnetic orientation of the layer from down to up. This is a game changer. It means we can use one spin current to control another magnetic component, effectively using spin to control spin. This is the spintronic equivalent of how a transistor uses a small charge on its gate to control a large current flow. It allows us to build all spin logic gates and memory cells that can be written to purely with electrical currents, making them fast, scalable, and energy efficient. We are no longer just passive observers of spin. We are active manipulators, capable of setting and resetting spin states with precision. These methods, spin filtering to create polarized currents, spin-dependent scattering to read states, and spin transfer torque to write states, form the fundamental toolkit of the spintronic engineer. Combining these tools lets us process information with both charge and spin, fundamentally expanding electronics. We are not just making the existing switches smaller. We are building a new kind of switch, one that speaks the rich, nuanced language of quantum mechanics. The age of simply pushing charge around is giving way to a more subtle and powerful era of controlling the quantum compass within every electron. Up next, giant magnetoresistance, devices, and real applications. The Eureka moment, giant magnetoresistance. Spintronics' breakthrough came in 1988 when two teams independently made a discovery. Albert Fert, French physicist, Peter Grunberg, German physicist. They stumbled on a spectacular new phenomenon, experimenting with materials engineered at the nanoscale, sandwiches of alternating layers, magnetic layers, non-magnetic layers, layers just a few atoms thick. They studied nanometer-scale stacks, a magnetic layer, an ultra-thin non-magnetic spacer, and another magnetic layer. They could control each layer's magnetic orientation independently. Aligned, both layers point the same way. Anti-aligned, layers point opposite ways. They passed current through the stack and measured resistance. The change in resistance between the two states was dramatic. Aligned, recherche low resistance. Electrons, spin up. Electrons, spin down. Spin-up electrons pass easily when layers point up. Anti-aligned, resistance skyrockets. No electron has an easy path. Spin-up scattered by second layer. Spin-down scattered by first layer. This huge effect was dubbed giant magnetoresistance, GMR. It perfectly embodies spintronics, magnetic state, electrical signal. Low resistance reads as 0. High resistance reads as 1. Fert and Grunberg created a sensitive magnetic switch and a perfect spin detector. Their discovery enabled powerful new electronic devices. They were jointly awarded the Nobel Prize in Physics in 2007. Building a better hard drive. The discovery of giant magnetoresistance happened at the perfect time. By the early 1990s, the digital age was dawning, and humanity was beginning to generate and store data at an ever-increasing rate. The demand for computer storage was exploding. At the time, hard disk drives stored information as tiny magnetic regions on a spinning platter. A 1 was represented by a region magnetized in one direction, and a 0 by a region magnetized in the opposite direction. To read this data, a tiny electromagnetic head would fly just over the surface of the platter, sensing the faint magnetic fields from these bits. But as the bits got smaller and smaller, their magnetic fields became weaker and weaker. The existing redheads were simply not sensitive enough to detect these vanishingly small magnetic fields. The industry was hitting a wall. To store more data, you needed to shrink the bits, but if you shrank the bits, you could no longer read them. This is where GMR changed everything. Engineers quickly realized that a GMR sensor was the perfect tool for the job. They designed a new kind of redhead, known as a spin valve, based on the exact layered structure that Furt and Grunberg had pioneered. This new redhead was orders of magnitude more sensitive to magnetic fields than anything that had come before. Here's how it works. The spin valve read head uses a GMR stack, one pinned reference layer and one free layer that flips easily under tiny external magnetic fields. As this head flew over the spinning disk, the tiny magnetic field from a data bit on the platter would flip the orientation of the free layer. If the bit was a 1, the free layer would align with the reference layer, causing a drop in resistance. If the bit was a 0, it would become anti-aligned, causing a spike in resistance. A simple electronic circuit could then detect this change in resistance and interpret it as a 1 or a 0. The impact was immediate and profound. With GMR red heads, hard drive manufacturers could suddenly make the magnetic bits on their platters dramatically smaller and pack them closer together, because even the faintest magnetic whisper could now be heard loud and clear. Hard drive storage capacity, which had been growing at a steady pace, suddenly went vertical. Within a decade, the amount of data you could store on a standard hard drive increased by more than 1,000 times. Every time you download a movie, save a high-resolution photo, or access a cloud server, you rely on a direct descendant of this Nobel-winning Spintronic discovery. GMR helped make today's data-rich world possible. The success of GMR in hard drives proved that Spintronics was a commercial reality. The next logical step was to apply these principles not just to data storage, but to computer memory. As we saw, the most common type of computer memory, DRAM, is volatile. It forgets everything as soon as the power is turned off, and it constantly consumes power just to remember what it's supposed to be doing. Spintronics offers a tantalizing alternative: magnetoresistive random access memory, or MRAM. MRAM aims to combine the speed of DRAM with the non-volatility of hard drive storage, creating a kind of universal memory. An MRAM cell is built using a spintronic component called a magnetic tunnel junction, or MTJ. This is the next-generation cousin of the GMR stack. Like GMR, it has two magnetic layers, one pinned and one free. But instead of a metallic spacer, the two layers are separated by an ultra-thin insulating barrier, just a nanometer or so thick. Electrons cannot flow through this barrier in the classical sense. Instead, they must tunnel through it, a purely quantum mechanical effect. The probability of this tunneling depends on the spin of the electron and on the alignment of the two magnetic layers. When the two magnetic layers are aligned, spin-up electrons have a high tunneling probability. Spin-down electrons do too. This results in a low resistance state. Red is a 0. When the layers are anti-aligned, the tunneling probability drops dramatically. That creates a high resistance state. Red is a 1. To write data, we use the spin transfer torque effect. Passing a spin-polarized current through the MTJ applies a torque that flips the free layer's orientation, switching the cell from 1 to 0 or vice versa. Because the information is stored in magnetic orientation, it is permanent, non-volatile. Once a bit is written, it stays written, even if you cut the power. This has incredible implications. Imagine a computer that could turn on instantly with no boot-up sequence. Imagine a phone whose battery lasts for weeks instead of a day. MRAM is already used in niche applications where reliability and endurance matter: satellites, industrial controllers, enterprise storage. As manufacturing matures, MRAM could replace DRAM and flash memory, reshaping our computer's memory hierarchy. The same extreme sensitivity that makes GMR and MTJ devices perfect for reading data also makes them exceptional sensors for a huge variety of other applications. Any physical phenomenon that can be translated into a magnetic field can, in principle, be measured with incredible precision by a spintronic sensor. This has opened up a world of possibilities far beyond the confines of the computer. In the automotive industry, for example, spintronic sensors are everywhere. Anti-lock braking systems use them to track wheel speed with pinpoint accuracy. A toothed ring on the wheel hub rotates past a spintronic sensor, outputting a digital pulse train. These sensors work by mounting a multipole magnet on the rotating wheel hub. As the wheel turns, the passing north and south poles create a fluctuating magnetic field. A stationary spintronic sensor detects those fluctuations and converts them into a precise digital signal showing wheel speed, small, robust, no moving parts, ideal for harsh vehicle environments, crankshaft position sensing, camshaft position sensing, electronic power steering systems, compasses for navigation. Beyond the automotive world, spintronic sensors are finding their way into biology and medicine. Scientists are developing biosensors that use magnetic nanoparticles as tags. These tiny magnetic markers can be designed to attach to specific biological molecules, such as viruses or cancer cells. A highly sensitive spintronic sensor can then detect the faint magnetic fields from captured nanoparticles, allowing rapid, low-cost diagnosis from a single drop of blood, moving tests out of big labs and into the doctor's office or even into the home. Industrial automation, measuring robotic arm position, geoscience, detecting minute variations in the Earth's magnetic field. Spintronics is providing a new set of eyes and ears to the technological world. These devices are the unsung heroes of the spintronic revolution. By controlling electron spin, we not only compute and store data, but we have also gained a powerful new tool to measure and interact with the physical world with unprecedented sensitivity. While GMR and MRAM represent the first and second waves of spintronics, researchers are already hard at work on the third wave, pushing the boundaries of what is possible. One of the most exciting frontiers is the field of magnonics. If spintronics is about controlling individual electron spins, magnonics is about controlling the collective waves of spin that can travel through a magnetic material. These waves are called spin waves, and their quantum mechanical particle equivalent is known as a magnon. Unlike an electrical current, which involves moving electrons that collide and generate heat, a spin wave can transport information without any movement of charge at all. This is a profoundly important idea. It suggests we could build computer circuits where information is processed by these spin waves. Signals could be transmitted and processed with almost no heat dissipation, overcoming the heat wall that plagues conventional electronics. Researchers are already building basic magnonic logic gates, the ands, ors, and nots that operate using interacting spin waves instead of electrical currents. This could lead to a new class of ultra-low power processors, fundamentally different from the silicon transistors we use today. Another major goal is to create true spin-based logic. Instead of using transistors to control charge, we could use a spin transistor to control the flow of spin itself. In such a device, a small electrical or magnetic field applied to a gate would modulate the spin polarization of a current, not just its magnitude. This would allow us to perform logic operations directly using the spin property of electrons, integrating data storage, magnetic state, and data processing, spin logic, in the same device. This could lead to incredibly dense and efficient computing architectures, perfect for the massive parallel processing required by artificial intelligence. It is important to note that this is not quantum computing. A quantum computer uses delicate states of superposition and entanglement to perform calculations in a completely different way. Spintronics, even in these advanced forms, still largely operates on classical bits, a definite 1 or 0 represented by spin, but it uses quantum mechanical effects to read, write, and process them in new and powerful ways. The research into magnonics, spin waves, and all-spin logic is still in its early days, but it shows just how much untapped potential remains within the quantum world of the electron. It is a clear signal that the spintronic revolution is not over, it is just getting started. We have journeyed from the familiar world of electrical charge to the strange and beautiful quantum domain of electron spin. We have seen that the very devices we use every day, from our computers to our cars, are already powered by the first fruits of this quiet revolution. Spintronics is not a distant, futuristic fantasy. It is a real and powerful technology that has reshaped our digital lives. The discovery of giant magnetoresistance did more than just win a Nobel Prize. It unlocked the era of big data, allowing vast libraries to fit in the palm of our hand. It was the first powerful demonstration of a profound idea. There is more to the electron than we once thought. The promise of spintronics is as simple as it is transformative. By harnessing the electron's charge and harnessing its spin, we can design computers that are fundamentally more efficient. Imagine devices that consume a fraction of the power they do today, where batteries last for weeks, not hours. This is the promise of lower power, born from flipping a spin instead of pushing a current. Imagine computers that run cool to the touch, no matter how hard they are working. This is the promise of reduced heat, moving away from heat-generating charge currents to the physics of spin. And perhaps most profoundly, imagine a digital world without the constant hum of wasted energy. Non-volatile spintronic memory like MRAM could hold information with zero power. That would eliminate the energy drain of refreshing volatile memory across phones and massive data centers. Lower power, less heat, non-volatility, faster data access. This combination is not just incremental, it is a paradigm shift as Moore's law slows. Spintronics solves computing's biggest limits, heat and power. As AI grows, charge-based designs hit walls. Spin-based methods offer elegant, efficient alternatives. Spintronics offers a way to leap over these walls, not by brute force, but by embracing a deeper, more complete understanding of the quantum nature of the electron. It is a promise of a smarter, more sustainable digital future, written in the language of spin. For all its incredible promise, the spintronic revolution is not yet complete. The path from a laboratory breakthrough to a globally manufactured technology is long and fraught with challenges. While spintronic sensors and hard drive read heads are mature technologies, building entire processors and memory systems based on spin is a far more complex endeavor. One of the biggest hurdles is the efficient creation and detection of spin currents. We need to be able to generate currents that are nearly 100% spin polarized and read their state with perfect fidelity. While we have good methods, improving their efficiency is a major focus of current research. The materials themselves present another significant challenge. The perfect spintronic material would be easy to manufacture. It would work flawlessly at room temperature, and it would allow spins to travel long distances without losing their orientation. Finding materials that tick all of these boxes is incredibly difficult. Many exciting spintronic effects have first been discovered only at cryogenic temperatures, or in exotic, hard-to-produce materials. The ongoing quest for new material systems, novel alloys, two-dimensional materials like graphene, is at the very heart of making widespread spintronic computing a practical reality. Scalability and manufacturing complexity are the final, crucial pieces of the puzzle. These challenges are not reasons for pessimism. This is not science fiction. This is the real, painstaking work of engineering at the atomic scale. Researchers around the world are tackling these problems every day. Realistic timelines are measured in years and decades, not months. The third wave of spintronics, spin-based logic, magnonic processors, is still on the horizon. But the second wave, with MRAM, is already beginning to reshape the memory landscape. The progress is real and measurable, and so our story ends where it began, with the humble electron. For a century, we treated it as a simple point of charge, and with that one idea, we built a civilization. Now we stand at the threshold of a new understanding. The journey to unlock the full power of electron spin will be one of the great scientific and engineering adventures of the 21st century. It is a quiet quantum revolution, unfolding not with a bang, but with the silent, subtle flip of a spin in a circuit. And it is a revolution that is well worth watching.